What did you say? Say hello. Okay. Let's try to finish this chapter and then get into another topic today. So, just a refresher, we didn't go very far with sampling and sample preparation, but hey, before I get started, happy Monday. I'm not standing between you and weekend.
The entire
What's that?
between me and the entire week.
What do you have against me? I mean, what have I ever done to you? Okay. Well, I wish you a very pleasant week. Okay. So what is sampling plan? Do you remember when we talked about it last time? What does it mean when you hear sampling plan? Or what can be part of a sampling plan? I thought Katie had her hand up for a second. Okay. Emma.
Application coming from gather some process.
Yes, you start with how to plan to gather samples. What else do sampling plan should include? How to gather it, that's one, but what else do you want to determine? Yes, Mary. Sample size. How many samples I need to take out so that I have enough representative samples of the entire population? Okay, so how to get the samples, how many samples, what else is important? Sampling, right? So what else is important? Sample prep. Sorry, you were going to say. What's that?
Controlling variables.
Controlling variables, especially when you're preparing the samples, you don't want to change anything about your sample that might impact your results. So how am I going to transport these samples? How I'm going to store these samples in a way that it won't impact its characteristics? So you determine all of that once you know the purpose of why you're sampling anyway. So are you sampling for attribute or variable component? And then we'll talk about that in a minute. So that will help you determine how many samples you should get out. And there are other questions in those tables that I shared. Like I said, it's FYI. I will not really go deep and ask you these questions, but you really need to know certain things about the objective of your analyses, the type of samples that you have, what you will be analyzing, and then you will be able to determine or put together a sampling plan. It is very important. Sample plan is almost more important than the actual analysis. And why is that, do you think? Why is sampling plan very, very critical to you as an analyst? Give it a go, Lizzie.
Helps like make sure that you're getting a good representation of the whole.
Yes, good representation, accurate results, good assumptions that you can trust, low risk assumptions. So if you mess up sampling or how you prepare your sample, your results, no matter how good of an analyst you are, your results will be erroneous. Although, like I said, this is a dry topic, but it's a very important topic in analysis, is how do we sample to put a sampling plan. Okay, and then all of these other questions in gray, we'll cover them later, and these will be good study questions. All right, so there are two types of sampling. One, we call it attribute sampling, and another is variable sampling. So when you hear attribute, you are really looking for mostly the presence or absence, or something that is randomly distributed. Let's say you have mold. Sometimes you have like a piece of bread, and then there's only mold on the corner of that piece of bread. Or sometimes you don't see that mold by your eyes. So, but then it's not really something quite dispersed, normally dispersed, or homogeneously dispersed in your sample. And that mold can give you aflatoxin, for example. And aflatoxin should not be in the food. There's zero tolerance. So when you have such an attribute that you're looking for, a particular component that is not really distributed, like in a bag of flour, it's a very homogeneous sample. So if you're looking for protein, protein is normally distributed, or ash content, or carbohydrate. It's normally distributed in your sample. But when something is random and can be present anywhere, it is, in that case, you really have to take large sample size. So meaning very many samples from different locations is what you need to do, because there is a high risk. For example, is aflatoxin or Clostridium botulinum. There is high risk to the consumer. You don't want to miss it. If it's there, you don't want to miss it. So you take a lot of samples. So you will have multiple replications, very many replications. And then you check the presence or absence of that and decide whether or not it's acceptable. And here's like an example, Clostridium botulinum or aflatoxin from mold infection. So here's it just show you kind of a diagram. If you have an organism of concern or a component of concern, certain pesticide or antibiotics, let's say, or aflatoxin, these can be randomly distributed, but they shouldn't be in the food. Some pesticide, there is a limit of concentration that can be accepted, but other pesticide you should not have any of. So, so basically you would measure their presence, and sometimes aflatoxin, no, you should have zero aflatoxin. So if you can measure aflatoxin, for example, then you reject the sample. If sometimes you have a defect action level or a minimum allowable or a maximum allowable amount, then you would go, okay, so it is less than 5 parts per million, for example. So yes, we accept. So it really depends on the component. Then the variable sampling, this is really simple, is when you're looking for a component that is homogeneously present in your sample or normally distributed. Here you don't take that many number of replications. There is a set number of replications that you would do depending on the purpose of the analysis. So usually it's a quantitative estimate. So it's not just presence or absence. You actually get a concentration most of the time, or a relative percentage, or a number, basically, a quantitative number on a continuous scale. And then you decide acceptability. So sometimes your acceptability is decided whether or not it fits the range that is accepted for a standard of identity, for example. We give that example a lot, like milk has a standard of identity, fat content should be within a specific range to claim that it's whole milk, and so on. And here, examples of these continuous scale measurement could be color, a physical measurement. It could be a total solid measurement. It could be a component measurement like salt. All right. So the number of replication really depends on the purpose of the method, and also sampling costs. Is it going to be more expensive to run 20 samples versus 10 samples? So you have to make that decision. But also sometimes you are bound by regulation. Meaning, if we are doing composition analysis for nutrition label, you have to have a minimum number of replication. So the FDA and FSIS require at least 12 different samples that you collect from a lot. Let's say you have a box of cans of beans, and then you have 100 cans of beans, and that's for simplicity. Then you have to randomly select 12 samples. You can open all the 12 cans and combine them to have a composite sample. So you have 12 cans that you selected, then you can combine them. And once they're homogeneously combined, you can take 6 subsamples. And that's the minimum you need to do composition analysis for your nutritional label. Okay. So sampling plan by, if you're doing acceptance sampling, so let's say you are measuring certain quality characteristics, and then you have a certain set of samples that you are testing, and you're allowed to have 5 defects, let's say, or 5 to 10 defects are acceptable. Below 5, you accept. Above 5, you reject, for example. So you would run your analyses on these set of samples. So N is for the number of samples you pick out for analysis, and C is number of defects. Okay. So N is number of samples, C is number of defects. If your testing is below the number of defects that are acceptable, you accept it. If it's above, you reject. And that is called a single sampling plan. Below, accept. Above, reject. But then sometimes you are allowed to have a range. So your value is within what is accepted and what is rejected. So you do testing again. That's called the double acceptance. Sequential sampling is a little bit more complex, but basically you sample until the number of defects is above a certain amount, so you reject, or you continue sampling, and no matter what, your defects is always lower, so you will be in this side of the graph, and then you would accept. So yeah, just take it as it is. Don't think too much about it, but that's what is sequential sampling. When you need to learn these, or when you need to apply this, you have a lot of references to go back and figure out, should I do single, should I do double, should I do sequential? Here, just know the difference. But later on, when you have to apply them, you have lots of resources to go back and know which ones to use. Okay. So we just talked a little bit about mycotoxin, and here's an example when it is monitoring level of mycotoxins, and you want to measure that. So do we need many randomly selected samples? Is a single sample plan used? Is sampling error many times greater than analytical error? What do you think? A is for sure. But what about C, for example? If you do a sampling error, you are really having a very high risk in either accepting something that has mycotoxin, that's a safety risk for the consumer, or potentially, well, the risk higher for the consumer at this point. I'll talk about producers' risk in a minute. But single sampling plan is what you usually use. Here's why. Because first of all, you take a set of large number of samples, and if you have 0, great, you accept. If you have 1 sample that has mycotoxin, you reject. Okay. So we have 2 risks usually for your decision making. One is a consumer risk. Second is a producer or vendor risk. The consumer risk is to accept a lot that is potentially of poor quality for the population, especially when it's safety related. This should be less than 5%. Your risk of accepting a bad quality lot should be less than 5%. However, there's also risk of rejecting a lot because losing money. You might be rejecting a lot that was totally fine. You just did a mistake and you rejected it. This risk is a little, you have a little more wiggle room, but it should still be low, between 5 and 10% or less than 10%. Okay, so what you really need to remember is your sampling plan should be simple and flexible, so you change according to the needs. You have to protect both the consumers and the vendors, and also ensure reliability of your results. So this is what you really need to remember, 3 important factors about your sample plan. Okay, so I'm going to give you an example of how to pick out sample from a bag of or a sack of flour like that. Assume you are producing, or the company is producing, for simplicity, 100 bags of flour a day. And then you need to do your quality assessment. So what you do, you can't analyze all 100 bags, but what you can do is you take the square root of the number of bags. So if you have 100, you pick 10. And the way you pick them is randomly with a statistic. So you give them random numbers and you get a random number tables, give those bags numbers, and then you select 10 random numbers. And then those 10 bags, you can take a sample from a corner opposite to the center or diagonal to the center, and then from another corner opposite to that corner. So if the center is here, you take 2 samples from 2 opposite corners to the center. And then you store in clean, dry, well-sealed container for later analysis. And that is the official method for sampling flour. That's an example. So again, there will be a specific way of sampling depending on the product. You will know that through references later on if you have to determine that. So it's very easy to sample from a homogeneous sample. It means it's all same particle size, let's say, all homogeneous consistency like the flour, but sometimes you have samples that are heterogeneous. So different components of the food is distributed unevenly. So this way you would have to take samples from multiple locations. But often what you would do is make sure before you do any analysis, take your sample that you collected from multiple locations, make it a composite, and homogenize it. So for example, if you are doing your capstone and you are determining the composition of a nutrition bar, so in this, or high protein bar or what have you, this bar has in it a lot of different components. There are nuts, there are fruits, there are caramel, for example. The best way you would do that is you grind it while frozen, so that it doesn't get sticky. So cryogrind, and we'll talk about that in a little bit. And then it will be homogeneous, and then you can sample from that for your analysis. So sampling, when you have mechanical sampling, it's less biased. So whenever you're able to have mechanical sampling where there's no human bias, you would do that. Sometimes if you can't, you just do manual sampling. In line of process, oftentimes sampling is done mechanically to reduce bias. So we have non-probability sampling and then statistic-based sampling. If you're able, whenever you're able, you want to do probability sampling or based on statistical randomization, but sometimes you can't. So let's say you have this truck, there's no way to randomize and select a truckload of grains. you just rely on judgment sampling. Sometimes you have a silo of grains. You have your corn silo. You can only take from the top. So restricted sampling. But there is no way around it. The probability sampling, whenever possible, is the way to go. Random sampling, like I said, with the example of the sacks of flour, or if you have a box of cans, then you would give them random numbers and select the numbers randomly. So that's random sampling. This is the best way of sampling. And then there is systemic sampling that is mostly applied for online during processing sampling. Let's say you have milk going or cream or what have you, and then every certain interval, a mechanical sampling unit is used to take out a sample. So it would be after a set number of samples or weight or volume or time. Okay. Stratified sampling, I'll give you two examples. One, let's say a company produces tomato soup. So, and you have 100 different branches across the US. Then you would say, okay, I will stratify based on the number of locations, based on the locations, and within each location, I will randomly take a set number of samples to analyze using random sampling. That's one example. Another example, you have one company, but you have two shifts. People shift working, producing a certain amount of sample, and let's say the night shift producing another amount of sample. So you will have two, each would be one strata. Then you would take random samples from each shift. That's called stratified sampling. Cluster sampling, and usually the example of the 100 different locations of plants producing those canned soup, there are a lot of locations. What you can do is you can consider each location as a cluster and randomly select 10 locations. Instead of analyzing samples from 100 locations, each time you pick 10 locations, and from each location you take samples using randomized sample. These examples are in your book. So in the book, you can find similar examples. Okay. The composite sampling is what I just told you, the example of, for composition analysis, you take 12 random samples and you make them into one composite sample. And from that composite sample, you take 6 subreps. And that's very common in analysis for nutrition label. Okay. So what about this one? The following are potential problems associated with sampling that may result in reduced reliability. When in doubt, yes. So when you have no choice but getting samples that are conveniently reachable, that is a problem because you might have issues with the samples you were not able to reach in a container. Poor storage, obviously, high moisture, high temperature, or high humidity, high temperature will change the composition of your sample. Mislabeling, obviously. So that is very silly, but very common mistake. Okay. Homogenizing your sample is very important for determining certain components. So you need to have them homogenized. So oftentimes we do grinding. And we need to get to a certain mesh size. Remember, the mesh is number of opening per linear inch. So For certain analyses, you require a minimum of 20 mesh, meaning 20 opening in 1 linear inch. And that's for common moisture, protein, mineral determination. But sometimes you need smaller particles, like if you're extracting fat, for example, you really need smaller mesh, meaning a larger mesh number, meaning smaller pore sizes, smaller particles. So 40 openings per 1 linear inch. So we grind and we sift to determine the size of your particles. But also, like I said, examples, sometimes if your sample is high in moisture or high in sticky material, your really best way to grind it is when it's frozen. Or if you know the moisture content, you can dry it, like by freeze drying, for example. You can take your sample that is high in moisture, sticky, you can put it in the freeze dryer, take it out, and then grind it dry. But then you always have to account for the moisture. One thing you can do, you can weigh the sample before you put it in the freeze dryer, take it out, weigh it again, so you can account for the moisture content. So remember this for your capstone. Also, I remember something with capstone. A few years ago, I saw a group in the lab trying to analyze fat content using a method that you will learn called Mojonier. So it has a specific flask. It's like a banana-shaped flask. So they wanted to determine fat content in potato chips. So I walked in randomly and I saw them, putting all their solvents and doing the right thing, shaking it and all of that. I look inside, I see a whole potato chip there. I was like, you guys, what are you doing? We're extracting fat. How are you extracting fat? The potato chip, all that's like this big chunks of potato chip. Don't do that. You will not be able to extract your potato chip like that. Besides, you have to digest first with acid. So it was a hot mess for a second. Okay. Um, So we really need to change to make sure that the sample does not change in composition. So sometimes you have endogenous enzymes in your sample. Let's say, flour has lipoxygenases, lipases. You don't want them to sit there and digest your fat and oxidize your fat. So you want to make sure enzymes don't function during preparation and during storage. Okay, so how do we prevent enzymes from working? What's that? We can deactivate. Yes, we can heat treat, deactivate, but sometimes heat can cause other damage. So if we're not able to heat, when we prepare the sample and we want to store it, what do we want to avoid? What what do enzymes like? What do they like to work? The right temperature, right? The right pH, the right moisture content. So you want to store your sample mostly in cool conditions, um, well packed. So you don't want to, you eliminate the air when possible. You might change the pH to acidic. And then you can dry the sample if that is not going to impact the characteristics that you're measuring. You can also put enzymes inhibitors or chemicals like sodium azide that will prevent enzyme activity. Okay. So different ways, but they have to be eliminated. Also, if we are determining, let's say, degree of saturated or unsaturated fatty acids, polyunsaturated, you don't want them to oxidize. So how do I avoid lipid oxidation? You prepared your sample, you put it in a container, What's the first thing you want to try to do? Huh? Remove? Yes. Remove air. We call it nitrogen flush. So you flush it with nitrogen, so nitrogen replaces the air that has oxygen, and you close. And you want to make sure you use containers that are not permeable to light. So avoid air, avoid light, avoid heat. Sometimes you add antioxidants as well if it's really important evaluation that you're making. You don't want microbial growth, obviously, because if you have microbes, they're going to eat up your carbohydrate, they're going to eat up your protein, they're going to ferment. So everything will be bad. They're going to produce their own metabolites, so you don't want that. So again, to limit microbes, what do you do to limit microbes from your sample? You can also tight seal. You can put antimicrobial agents, store in cool and dry conditions. All right. So no matter what you do, you really want to avoid sample alteration. That is number one rule in sample prep. Okay. So there is this question that is in your chapter in your book, and it's here. Try to solve it for an extra 5 points. Bring it to class next Monday and give it to our TAs. All right. So this is extra, it's not homework, kind of, it's homework, but not really required. But it's good to solve it and get extra credit for that. Okay. All right. So, any questions? All right. I promise this is the last dry material. What you think everything I teach is dry material. Emma, of course, thinking that inwardly. Okay, where is my mouth? Yes, yes. No, Monday. You're a week from today. Isn't today Monday? Yeah. Yeah, okay, a week from Monday. Yeah, yeah. What happened to my, there it is. All right. Now grab another piece of paper for another 5 points extra. And before you're not going to turn it in today, keep that sheet of paper with you because we're going to do calculations over this today and next on Wednesday. By the end of Wednesday lecture, take a picture of it and give it to the TA. We're going to solve questions in class. I'll give you the correct answers. I will even post on the website after the lecture on Wednesday. I will post the key of all calculation. Just so you get extra credit and practice your calculations, you turn these in, but you'll get the correct answers later. All right. So it's very important in analysis to be able to prepare your own reagents. Every analysis, you have different reagents associated with your experiment. So you really want to be capable in doing the right calculations so that you have the correct reagents and buffers. Sometimes you need buffers when you don't want the pH to change during a reaction, especially enzymatic reaction. So you really need to know how to do that. If you go to grad school, this is a must. Your advisor is not going to sit down with you and review your calculation. They're going to assume that you know how to do that. Also, if you go to industry and you're working in a lab, you are expected to know how to do these calculations. So some of these calculations are intuitive, you know them, you've done them in chemistry, general chem, and even in high school. So again, it's refresher and putting it in context of reagent prep for food analysis. And there will be a lab on reagents prep next week. So this week you're doing accuracy and precision. Next week, you will prepare your own reagents. You're going to do pre-calculations and come to lab. Your calculations will be checked, and you're going to prepare reagents that will be used in future labs. Okay, so that is the purpose of this topic. So what do we know about buffers? I know they're annoying, and I know people forget what buffers are. But what do you know? You can't go wrong. You can just say whatever you think is correct. All right, Scarlett.
A and B.
A and B, you said? Okay, hold that thought. What did you want to say, Marie?
I was gonna say A and C. Oh, sorry, A and C, not A and B.
All right, Scarlett, you got it. Okay, all right. Yes, A and C. Buffers can have any pH, really. But usually, not any, we don't prepare buffers that are pH 1 or buffer that is pH 14, the extremes, no. But sometimes your buffer is really a pH 4.6 buffer, or your buffer is a pH of 9, or your buffer is pH 7. So it really depends, and the components of the buffer help you with maintaining a desired pH. Okay, so there are different buffers that we can prepare for different pHs. Not the same buffer that can be used for any pH. It really depends on the pKa of the buffer, and then I will talk about pKa later. Okay, so, and it does consist of a mixture of weak acid and their conjugate base. So weak acids meaning acids that don't want to hesitate, they don't want to give you the protons very readily. Okay, so if we say weak acid, HCl is not a weak acid. It dissociates almost completely in water. So so you will have always dissociated H plus and dissociated Cl minus. But organic acids like ascorbic acid, lactic acid, citric acid, these are all organic acid and weak acids. They don't want to give you their H very readily. And their conjugate base is when they give out the H, that would be the conjugate base. So there will be CO minus or carrying a negative charge when they give out the H. So the base is really the salt of the acid. Okay, the salt of the acid is called conjugate base. So yeah, so the buffer, you have a combination of those. You have the weak acid and you have the conjugate base, and that's why they stabilize the pH. So when the pH changes, let's say you're titrating with acid and you have buffer, so as your protons go in the solution, your conjugate base is going to snatch that proton. If you're titrating with base, NaOH, for example, OH minus go into the solution, your conjugate acid is going to give a proton. So, and then stabilizes the pH. Okay, so the conjugate acid will give give an H when the pH tries to get to be more basic, and the conjugate base picks up the proton when the environment trying to become more acidic, and then the pH maintains. Okay, we'll talk more about that, but yeah, but that's the concept of stabilizing the pH. All right, here's the fun stuff. We need to remember these guys. All right, so molarity, it's known as number of solutes per liter. What? When someone having fun time is almost up. Well, at least I'm having. But Emma, are you enjoying the class? Okay, great. What did Gray say?
Yeah, I like them.
Yeah, where's Ellie? Oh, okay. So I'm gonna put it in equation form here. Molarity equals number of moles per liter. And number of moles equals mass by the molecular weight. And the molecular weight, let's say H2O has a molecular weight of 18. What does it stand for? So molecular weight, we have to always use units. So to cancel each other in an equation. So when you have molecular weight, it is, let's say, of water. It is 18 grams because oxygen is 16 and hydrogen is 1. You have 2 hydrogens. So it is 18 grams per mole. So that's the unit of the molecular weight. So if, let's say, I'm looking for the number of moles here, then if I have the weight in grams and the unit here grams per mole, then these will cancel and mole will go up. And then it would be the units for number of moles will be a mole. That's kind of why I always ask you when you solve any problem, make sure you put the units and then see if your units cancel. Then you will know if you did the right, if you use the right equation. Okay. Normality is number of moles equivalent of a solute. What does that mean? Sometimes it is you have multiple hydrogens or hydroxyl groups that are transferring in an equation. So H2SO4 has 2 hydrogens that can, or protons that can transfer, whereas HCl has 1 hydrogen. NaOH has 1 OH, but calcium hydroxide have 2 hydroxyls. So then you have to account for the number of moles equivalent of that solute. So for example, here I give you 1 mole of H2SO4 is equivalent to normal H2SO4. Sometimes your concentration is reported in normality, sometimes it's reported in molarity. And it's important to know if the molarity is equal to normality in the case of NaOH and HCl, and when the normality is twice as much as molarity when you have two H's or 2 OHs. Then there is this equivalent weight, which is important. It'll show up later when we talk about pH and titratable acidity. When we're trying to determine the acidity in juices, let's say, where the source of acid is organic acid, sometimes has multiple carboxyl groups. So the equation will include molecular equivalent weights. So hold on to that until we get to that chapter. Sometimes you report concentration as a percentage. It could be grams per 100 grams. A percentage is grams per 100 grams or grams per 100 milliliter or milliliters per 100 milliliters. Sometimes it is a volumetric concentration. Sometimes it's a mixture of grams in a volume. Sometimes it's grams to grams. But it is a percentage in 100 units. 1 unit in 100 units. Sometimes concentration is way much diluted. Like when we are doing caffeine, you have concentrations parts per million. When you're doing, let's say, if you're doing a flavor analysis, concentration is maybe even parts per trillion or less. So parts per million is equivalent to the most common one that you would see is microgram per milliliter. That's a very common and that's parts per million. Or milligrams per liter, or milligrams per kilogram. That's part per million. Because you have 1 million micrograms in 1 ml. That's what it means. 1 million micrograms. Well, parts per million. Gosh, it's 1 in a million. I don't know how to say it right without confusing you, but in 1 gram, you have a 1 million parts, micrograms. Yeah. So we'll do this and then we'll let you go. Okay, so equation of neutralization is very, very important. We use it a lot, whether for diluting of solutions or whether it's an acid-base reaction, or we use it when we're trying to get a concentration using titration, anything. It doesn't have to be acid-base. We'll use it a lot later on. There will be a lot of examples where milliequivalent is used. So at equilibrium, milliequivalent of one reactant equal to milliequilibrium of another. And usually it is milliliter of a specific component times its normality at equilibrium equals milliliter of the other component times its normality. So, like I said, it's very common to you. We use this for dilutions protocol. So if you have a concentrated HCl, bottle of HCl, and you want to prepare a diluted solution from it. So in this example, usually when we buy HCl, the concentrated bottle is about 12 normal. That's its concentration. And often we have to prepare 0.1 normal HCl, and you will be doing that next week because we use that in the titration for protein analysis lab. So using this equation, how would you prepare 1 liter of 0.1 normal HCl? Take a couple of minutes. Do you want to do this now or do you want to do it on Wednesday? Can let you go. Wednesday? Yeah, we'll do it on Wednesday because it's at time and I don't want to rush you. All right, we'll continue on Wednesday.